So this time I want to tell about such thing as free fermions. So there is uh, 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 there can be several variants of this theory. So one option is to consider real free fermions. In this case, action is given by this expression psi d bar psi plus psi bar d psi bar, and mm, the question is what is the OP of psi of z and psi of w in this case? What do you think? Yes. So it is a matrix element of the inverse of d bar z w, and it is well, maybe with some factor, but it is easier to fix OPs than remember the precise coefficient in the action. So, and if you write psi of psi bar of z bar, psi bar w bar, it will be 1 over z bar minus w bar, of course. So let's compute a central charge of this theory. So well, in principle, we can derive the action. We can derive an environmental tensor from the action, but taking into account that psi has dimension 1/2, so that it is conformally invariant. 1/2 0. But it is easier just to guess on this. So let us say that T of z is so what can we write of dimension 2? First, it should be quadratic in psi, and it should have dimension 2. So the only option is actually psi d psi. Psi d psi, normally ordered, with some coefficient. If I remember correctly, it is minus 1/2. And let us check the OP of T of z with first with psi and then with itself. So T of z with psi of w is so it's minus 1/2 psi of z, d of 1 of z minus w plus 1/2 1 over z minus w d psi of z. So it is 1/2 psi of z over z minus w squared plus 1/2 d psi of z over z minus w. So if we now expand it around w, it will give 1/2 psi of z, psi of w, over z minus w squared plus d psi of w over z minus w plus regular. And here also plus regular. And if we want to compute central charge, we should compute OP of T of Z with T of W. So it is 1/4. And then, so it is psi of Z, d psi of Z, psi of W, d psi of W. So it is minus 1/4, 1 over Z minus W, d psi of Z, d psi of W. Or maybe it was not a very good idea to compute this, but anyway, let us finish. So there are 4 terms which are quadratic in psi, and there are also 2 constant terms. Plus 1/4 dz 1 over z minus w, dw 1 over z minus w, minus 1/4. So now let us start to expand everything around the second point. This first term is minus 1/4 1 over z minus w. So when we try to expand it around the second point, it becomes just 0, because when because so this whole is normally ordered. So normally ordered psi squared is 0, because it is fermionic. So this first term goes to 0. About this second term, we can just uh, uh, so we should write two terms of this Taylor series. Um so we have 1/4 1 over z minus w squared, and uh, one term here is d psi of w, and another term is d2 psi of w, z minus w. So oh, so we should have first looked at this term. So it was a second one here, minus 1/4 when more z minus w squared, and we should expand this. So it is psi of w, d psi of w, and the second term where we try to compute d psi of w squared, it will be 0. So it's just one one term coming from here. Now about this one. So this derivative will equal to 2 over z minus w cubed, minus 2 over z minus w cubed. So total it is 1/2 1 over z minus w cubed, and here we have only one relevant um, expression, which is z minus w and d psi of w, which comes from expansion of this psi of z. And now let's go to this part. So this gives 1 over z minus z minus w squared with minus sign. This was with plus sign. So it is so it is minus 1/4 1 over z minus w fourth, and this term gives so when we differentiate for the first time, it gives 1 over z minus w squared. When we differentiate for second time, it gives minus 2 over z minus w cubed. So in total, it is plus 1/2 over 1 over z minus w fourth. So let us finish this computation. So so what we have in total? We have so in these two terms cancel each other, this one and this one. So we have mm, uh, plus mm, plus this term. And plus plus this component which contains a central charge, 1/4 z minus w to force power. And now let us look at this formula. Uh, so, well, I actually don't like the powers which we obtained here. Hmm. Because in principle it should be dt over z minus w plus 2t over z minus w squared. Well, I see the mistake, at least one mistake. So mistake is here because I thought that these two terms cancel each other, but actually they are opposite because here we have dip psi times psi, and here is psi dip psi. So so it is actually in the same term. This one, this one, and this one. So altogether, it gives dip psi times psi over z minus w squared. And now the question is uh, about this second term with second derivative, and the question is if we wrote all such terms, or could we miss something? Yeah, we actually missed another term here because it came from what expression. It came from here. So in principle, we should expand this further. We have 1 over z minus w cubed. So we should expand this first psi up to second order. So because of this, we have another piece here, z minus w squared due to psi of w, psi of w. So we also have this term here, and if you combine it with another bracket, it will give a coefficient one half here. And yes, after we fix this, we see that this is precisely dt, so we can write an argument of tensor as one half dip psi times psi. And this is dt because dip psi squared is 0. Only ordered. So it is dt, it is 2t, of course. So follows from here that the central charge of this fermions is one half. And it corresponds to minimal model M34. As I remember. We can also consider complex fermions. In this case, there is psi star and psi, and there are also complex conjugate operators. Psi star bar, d psi bar. So in total, we have 4 fields, two homomorphic and two anti-homomorphic. So what do you think are the OPs of this fermions now? Like, what is the OP of psi of z with psi of w, and psi star of z with psi of w? Mm-hmm. Mm-hmm. Y module squared. No, it's psi star and psi. They're who is complex conjugate? This? Hmm? No. Because so a equation satisfied by them is d bar psi equals to 0, d bar psi star equals to 0, d psi bar equals to 0, d psi bar star equals to 0. So star is kind of charge conjugation, not complex conjugation, which is so complex conjugation is something like p symmetry, and pt probably is z to minus z, so something like this. So it's a c symmetry, not something related to coordinates. So, but so we have some matrix. We have a matrix like 0, d bar, d bar. And when we take inverse of this matrix, it will give us actually we should if we want to write it as a symmetric expression, then it should be something like c star, type star, psi, 0, d bar, 0, c star, psi. So if you compute the inverse of this matrix, it will equal to 0, d bar inverse is 0. So what we should get in the corners, like for correlators of psi and psi star and psi, we should get this precise correlator of psi and psi in the previous problem. What do you think should be written here then? Yes. Yes. So the same for complex conjugate. But, if you want now to compute a central charge of the system, it is much easier to introduce kind of a real and a imaginary part of this fermions. So we can say that psi equals to psi maybe let's say that we have psi r, which is 1 over square root of 2 psi plus psi star. And we have psi I, which is 1 over I square root of 2 psi minus psi star. So now we see that OP of psi r was itself so psi r with psi I. What is the OP of psi r of the with psi I of W? I already wrote the answer. So, so mm, because OP of psi and psi star equals to 1 over the minus W, and this one also equals to 1 over the minus W. So together this cancels. But, what is OP psi r of the with psi I of W? With psi r W. Hmm? It's the same function. So if you want to uh, mm, mm, how to say this? Mm, so they are Grassmann variables. So we can write that psi of W, uh, psi star of z equals to minus 1 over z minus W. And if we now exchange z and W, if you want psi of z, psi star of W, we will get again 1 over z minus W. So, mhm, yes. And the same for psi I. So also we see that complex fermions uh, mm, is easy to expect can be written as a combination of two real fermions. And so a central charge of the system is therefore 1. Uh, so it is like oh, hmm, it reminds somehow charge of the free boson, and we will see quite soon that it's not a coincidence. So, but before this, let us think more about this fermions. So first we can compute their energy momentum tensor. So we know in principle that this energy momentum tensor is sum of energy momentum tensors for psi and psi r. So it is 1/2 d psi I plus 1/2 d psi r psi r. So it's 1/4 d psi plus d psi star psi plus psi star. Psi minus d psi star psi minus psi star. 1/4. And so there are terms d psi minus 1/4 because of this factor minus I. So we see that these terms d psi times psi cancel, and the only remaining terms are 1/4 d psi star, which becomes actually 1/2 d psi star times psi plus 1/2 d psi times psi star. And then momentum tensor. Okay, but about this theory, we say that the section, so as it should be in a theory of some charge particle, there is extra U1 symmetry. So there is this U1 which acts like psi star is mapped to e to I alpha psi and psi star, and psi maps to e2 minus I alpha psi. So if you want to compute the charge corresponding to this symmetry, we can just spoil this transformation. So let us consider S of E I alpha of x psi star e2 minus I alpha of x psi. This will equal to the integral. So this will equal to original action plus I minus I d bar alpha psi star psi from the first term. Well, and let us say that this let us say that we don't transform anti-homomorphic components. So looking at this expression, we see that there is a charge. So the charge corresponding to this transformation is psi star of z psi of z. And OP of this charge is of course consistent with this transformation. So J of Z with psi star of W is 1 over Z minus W. Psi star of W plus regular J of Z with psi of Z psi of W is minus 1 over Z minus W psi of W plus regular. So what tells to tell? So there is this charge. So psi star has a charge plus 1, psi has charge minus 1. But actually some similar phenomenon for the theory of free boson, namely, so So in the case of free boson, we had a charge J bosonic of the which was ID phi. We had so about coefficients. I'm not quite sure. We have exponentials e to I alpha phi of z, which maybe we can call v alpha, and the dimensions of these exponentials were alpha squared over 2. So we can call, so we can introduce here a charge of psi. Well, no, maybe it's bad notation. Just remember the charges of this psi psi star are 1 and minus 1. So it looks quite similar. Like if we take exponential e to I phi or e to minus I phi, we see that its charge one will have charge 1, another will have charge minus 1, and also dimensions coincide with dimensions of these fermions. So let us try to go further. So we have these two exponentials. So let us consider exponentials e to I phi of z and e to minus I phi of z minus I phi of z. To compare them with fermions, we need to check operator algebra. So, but what is the OPE of e to I phi of z with e to I phi of w? Oh, they're normally ordered. It is z minus w times e to I phi of z plus phi of w. So when z goes to w, there is it equals just to 0 plus plus something else, plus higher corrections. So we can say maybe that this OP is just regular. So it corresponds with what we have for the complex fermions. Mm. Now let us consider e to I phi of z, e to minus I phi of z. So who knows what in this OP? Of W. Hmm? Hmm? Uh, well, they're just exponentials. Hmm? Mhm. Hmm? Hmm? Which minus? No, the question, the main question is what is the power of z minus w? No, of course, because here we had kind of I, and here we have I and minus I. And e to I alpha phi of z, e to I beta phi of z of w is z minus w to alpha beta e to I alpha phi of z plus I beta phi of w. That follows from the formula for correlator. also from this formula. Hmm? So 1 over z minus w times what? Times I phi of z minus phi of w. But we can actually compute another term of this expansion. So it is what? It is 1 over z minus w plus we need to expand this as a Taylor series around w. And the first term of this expansion will give I d phi of w plus plus everything else. So, so this is the following, that operator algebra formed by these two exponentials, e to I phi and e to minus I phi, coincides with the operator algebra of fermions, of complex fermions. So, and also, so we had this this charge operator for the fermions. Normally order actually, and we can compare on this charge operators. So we can see what happens. So uh, this goes to. Well, we can write that psi star of z psi of w equals just by definition to uh, to 1 over z minus w singular term plus a CFT normal ordering psi star psi, which coincides in this case with fermionic normal ordering plus and so on. So we see that it is a fermionic U1 charge, a fermionic U1 current. Mm. And so this maps to this OP, like e to I phi of z e to minus I phi of w equal to 1 over z minus w plus I d phi of w. So if you compare these expressions, then we identify this psi star psi with bosonic U1 current. So it is I d phi. So J fermionic maps to J bosonic. So it was I d phi for the boson is psi star psi for the free fermion, and mm, it is actually clear why it happens so, because this U1 symmetry for the free boson corresponds to psi to phi shifted by some constant. And but if you do this with this formula for the free fermions, then e to I phi shifts to e to I phi times e to uh, to this constant e to IC. So this is it's actually the same symmetry, and so it's not a surprise that a corresponding corresponding currents also coincide. But uh, and on this correspondence between bosons and fermions is called bosonization or boson fermion correspondence. So it is known for quite a long time. So one possible application of this correspondence is a relation between Sine-Gordon and the Thirring model. Uh, so let us imagine that we want to compute the following partition function, probably with some sources. Uh, let us just let us say that we want to compute oh, want to compute some path integral, like integral in d psi d psi star d psi bar d psi bar star of the following object. So we write the action, which is psi star d bar psi plus psi bar star d psi bar, and so it is some conformal theory. But we also want to add some mass term for this theory, and so let me think which term to add. So let us add here psi bar psi bar star times times psi some mu plus psi bar psi star plus lambda psi psi star psi bar star psi bar. So it's so up to the choice of this mass term, which can be probably chosen differently. We can change basis in this fermion somehow, but I think it's kind of most generic action for this fermions, including a mass term interaction, and does not include higher derivatives. So, so we can only write for fermionic interaction, and this is called the Thirring model. So, and we also add some operators. One depending on this size, O(n) depending on size. So, so imagine that we want to compute something like this. But we can consider both of these terms which we added here not as a part of action, even this quadratic term. We can consider them as a perturbation. So let us rewrite this path integral as I can write it here. So we can write it as a d psi d psi star d psi bar d psi bar star. And well, let us say that this part of action is considered as a perturbation as a perturbation. So we consider it together with this operators. But if we do so, we can say that everything that is computed with this fermionic action can be computed using bosonic action if we perform all the substitutions in all these operators. So I'm saying that we can write this now as we first need to find what is the relation between this boson and fermion. In a sense, to write this full map, including anti-homomorphic fields. So we can tell that psi will be e to the I phi of z. Psi star will be e to minus I phi of z. We also need to write something for this bar component, and let us say that psi bar is e to I phi of z bar. Maybe so. We say that our phi there is some bosonic field phi of z bar, which is the sum of phi of z plus phi of z bar. And now this psi star will be psi bar will be this anti-homomorphic component of this field. Let me check if it is consistent with this formula. Maybe not very consistent. So let's choose here opposite sign. And suppose we have such freedom, because operator algebra will still be satisfied. And psi bar star is e to I phi of z bar. So if you now look at this action, then psi bar star psi will equal to e to the I phi of z bar. And that other term will be opposite, like psi bar psi psi star will be e to minus I phi z bar. Actually, here there should be some small tricks to make this fields anti-commuting, but this can be done at the level of zero modes. So it is not very hard. Oh, and if you now look at the last term, then we have literally a product of two currents. So we can say that so this is this psi star. Oh, sorry, I missed all the signs here. So psi star was with plus. So and this should be with plus, and this should be with minus. So psi star psi equals to d phi, and psi bar star psi bar will equal to minus I. So I d phi minus I d phi d bar phi. So no, maybe better to write that. Well, we can just write equal. Maybe better to say that it maps to under this Bosonic-fermionic correspondence. Maps to very well. So we know that if we make this substitution, then this path integral can be computed using this free boson. So it's integral over d phi e2, I will drop all these coefficients, like integral d phi, d bar phi, uh, uh, times, we need to write this perturbation terms. So this is e to mu e to I phi of z bar plus e to minus I phi z bar plus lambda and the product of these two terms d phi d bar phi and the separators O1 ON, and they should also be transformed according to this rule. So we see that this computation tells us that this quartic interaction becomes at the same term as at the action of a free boson, but it appears as a perturbation, not as a part of action. But now when we did this computation, we are free to combine these two terms, this one and this one. So it now becomes d phi e to, well, after some factors of pi and so on, but in general it is 1 plus lambda integral of d phi d bar phi e to the 2 mu cosine of phi and some operators. So but now if you want to make this field canonically normalized, we can divide it by square root of 1 plus lambda. So I can say that it is integral some other field, a normalized field d phi tilde d bar phi tilde plus mu integral of cosine of phi tilde over square root of 1 plus lambda. O1 ON. So uh, as a part of this correspondence, we can say that if this Thirring model was originally massless, then after bosonization it becomes just a free boson, and the role of the only role played by this interaction is a shift of conformal dimensions of all exponentials. So it scales all the fields, so dimensions will be different. And let me check. Camera. Hmm? Hmm? Because we normalized canonical term normalized kinetic term in the canonical way, and we obtained this factor in the exponentials, 1 over square root of 1 plus lambda. Hmm. Actually, this correspondence between Sine-Gordon and Thirring is used for study of Sine-Gordon, because here it is unclear what to do with this theory. It is something nonlinear, so on. But if you have Thirring, it is just a theory of some fermions with this current point interaction, and this can be solved using better answers. So. Um, if we find a relation between states in the Thirring model and Sine-Gordon soliton, then we can compute some scattering matrices for them. But I'm not going to do this. And so this massless version of this theory is also used in the description of the boundary of quantum Hall effect. So, yeah, so maybe maybe that's all about this correspondence. Do you have any questions about it? Mm, no. Well, it's the first answer, but let me think. Mm, I've never seen anything like this, but uh, I don't know if there is any fundamental reason why it cannot be done. Because naively it seems that we can try to remove one of the exponentials in this Thirring model, and uh, study only one of them. Well, the problem is that it is a kind of imaginary wheel, but at first it is not so bad theory. And second, we can play on this coefficient in the quartic term, and mm, mm, make this square root of 1 plus lambda imaginary. So no, I really I don't know. I never seen anything of this kind. Well, if we call a Liouville theory theory, well, if you call Liouville theory also the theory with imaginary exponential, then one special case, like c equals to 1, can be studied using mostly this fermionic approach. So conformal blocks can be constructed in a nicer way. So we can prove some Gaussian invariance in this theory. Actually, in several several different theories with different fusion rules. But for c equals to 1. Mm. But but it's done in a little bit different way, not directly from this correspondence. So no, I don't know. One should think about this idea. So people actually do different things. They consider they study this Saint Gordon not as a perturbation about the free field. They say that let us take one of the two exponentials and say that it is Liouville uh, and consider another exponent as a perturbation. Yes. But if talk about Liouville, then we have only one of the two exponents here, and in principle we can try to say that it comes from some variation of Thirring model. So probably it is a, Thirring model with so we can write Majorana and Dirac mass. And I don't know precisely who is who here. Looks like uh, one mass is so either they are opposite or one is zero and another is non-zero. So one should think about this. But yeah, it's an interesting question. Thank you. Uh, so which we have. Um, So let us now think about the following question. So we have this correspondence on the level of the operator algebra, right? But let me record. So we know that this field phi. Uh, oh, we know what happens with derivatives of phi. Like we know that d phi, I d phi is a sum of in over z to power n plus 1. And so in particular, it contains a0 over z. So, and we also know the following, that since there is this OP between, so this is J. Since J with psi star, J with phi, J with e to I phi is 1 over z minus w e to I phi. Then we see that we know that if uh, J if AZR acting on some state, let us call it Q. Then so we can say that so this can be written as a commutator of A0 with e to I phi is equal to e to I phi. So if this sorry, if the state is eigenvector for A0, then the state was variacted by the exponential, like e to I phi of z acting on q. So AZR acting on the state will give us q plus 1. So it tells us that this exponential of phi should contain some operator which shifts on this a charge by 1. So it means the following, that so we knew only this expansion for the current, and we need to recover the expansion for phi itself. So if I d phi is equal to this, then I phi is equal to what? It equals to sum of 2 minus a n over n z n from for n different from 0. Plus a0 logarithm of z plus some operator which I call q, and not to be confused uh, with that other q for ill will, but here is equals to 1, so we will not use this. So there should be some constant term, which a constant in the sense that it does not depend on z, and commutator of this term. So maybe we can write we can define it like this. So actually we have not this operator, but only exponential of this operator. So all these terms commute with a0, and this one does not commute. So this operator is responsible for zero, for this zero charge. So it shifts by one. Like this. So and having this, we can write a formula for for our e to I phi. So e to I phi, which is psi star of z, is so now we write a normal ordering of this exponents. So it is a sum over negative ends maybe how is it better to write this? Let's write it as 1 over n e minus n the n e to minus these two exponentials, then e to q, z to a0. And the same formula for psi of z. So it is e to minus I phi. So so if you write it this way, then there are some explicit operators which can act on the bosonic Fock space, and actually not on one bosonic Fock space. We have entire collection of these Fock spaces with eigenvalues of zero mode equal to integer numbers. So and as we remember, so L0 equals to A0 squared over 2 plus some A minus n an. And so dimensions of this highest vectors corresponding to different charges are q squared over 2. So so the picture is like this. So here we have 0 dimension, here we have 1/2, half. Here we have 2, and in general, such parabola. So this big thing is a harmonic Fock module. And it is a direct sum of bosonic Fock modules for each charge. So this, so these guys are bosonic Fock modules. So is it clear? Yes. Oh, we could do mm, canonic quantization of this free boson and see that this operator should appear. So it's one possibility. Another possibility is that we can look at the correlator of phi of z with phi of w. Uh, so so on one side we know that it is minus logarithm of z minus w plus in principle some infinite constant. And on the other side, we know that it is this expectation value of phi, which is sum of minus an over n zn plus a0 log of z wn plus w0 log of a0 log of w well, plus this constant plus q. And we say that on this right vacuum is killed by A0. So A0 acting on vacuum is 0. So we need to order the separators so that A0 kills this vacuum. And in principle, we should also order this ANs somehow. Mm, mm, so this surviving terms here are this these A's are positive and these A's are negative. Uh, and we can commute them. So it is sum over n greater than 0. Mm. An over n zn minus an over n zn from this term. A minus n over n w minus n 0 plus, so when we have a 0 squared, it acts on this vacuum by 0. When we have QA0, it also acts by 0. So the term which we need to take care of is A0. So it's log of z. 0, A0, Q0. Oh, we can write a commutator because because in the opposite direction they act by 0. So log of z times this. And plus in this term 0 to squared 0. So now this sum is minus sum over n greater than 0. I missed 0 over w to power w over z to power n. No, I didn't miss it. Sorry. Plus okay, so this is the logarithm. This first term is a logarithm of oh, there is a question about sign actually. It's a correlator of I phi with I phi, so it should be plus logarithm. Uh, we see that if you want to recover this correlator from the operator formalism, we should put commutator of A0 with Q equal to 1. Because this term with logarithm of z should combine with this term to give us a logarithm of z minus w. And about this constant, it's an interesting question because here we have this this expectation value of q squared, and it's not a very well defined object because who is our so what is the mechanical analogy of this problem? So this A0 is a momentum of the center of mass, and from here we see that q is coordinate of on the center of mass. Uh, so this vacuum wave function 0 is a wave function killed by momentum, so it is constant. Hmm. It's a kind of a constant as a function of coordinate, and this is expectation value of a square of coordinate on the constant wave function. So in principle, it is infinite, and it is this infrared divergence. But people say that we can this appears mostly in the exponentials, so we can just redefine them, removing this infrared divergence. But the essential part is this. So we see that Q is canonically conjugate to A0, and this is also consistent with this property that the separator e to the Q shifts momentum by 1. Uh, mm-hmm. Yes. Because it is a kind of integral of x of 1 times x squared dx over integral of 1 dx. So we have a wave function which equals to 1. It is a wave function corresponding to momentum 0. And so it's expectation value of x squared uh, on this constant wave function. But it is a known phenomenon. We saw that if if our theory lives on some sphere on the infinite plane without any boundary conditions, there is this zero mode, and integrals in this can diverge. But if we integrate, for example, exponentials, these divergences are a little bit nicer in the sense that they are delta functions which gives us conservation of momentum or of this U1 charge in target space momentum. Okay, so no, maybe that's all for today. Do you have any questions about this? Mm-hmm. Oh, it's a dimensions like hmm? Yes, yes. Because if you have so the question is what is the charge of a vacuum of some state which is killed by all components of psi and psi star. So the basic question is what is the LP of psi and psi star around z equals to 0. So we see that if a0 is non-integer, we will have non-integer powers in this expansion. It is actually useful in some cases, but generally 0 should be some regular point. So if there is a vacuum, then psi of z should be regular. So at least and also both of them should be regular. So for vacuum, we should have a0 equals to 0. Well, also the charge of the conformal dimension of vacuum should be 0. Yeah, all right. Well, actually, we should say about this fermionic Fock module, how precisely it is constructed. So, maybe it's better to tell this the next time. But well, in any case, so psi of z is expanded like this. So there are such expansions. So they are in integer powers of z, but indices, but there is this shift due to conformal dimension, and indices are also half integer. So if you consider a Fock module, uh, then it is a module generated from the vacuum, which is defined by the property that all positive modes of psi acting on this vacuum gives 0, and all positive modes of psi star acting on vacuum are also 0. Mm, so actually, we need to compute anti-commutation relations between the psi's and psi stars. Mm. By the way, can you tell this anti-commutation relation from the OP of psi and psi star? Like what should we write here? What do you mean by invert? What do you mean by invert? Mm-hmm. Yes. Mm-hmm. So you know the OP between psi and psi star. Uh, and what can you get from this OP for the anticommutator on of the modes? Hmm? Hmm? Yeah, but no, maybe it's better to do this next time or do it home. But P plus Q. Uh, but so it's also always this balancing condition, so that um, charges of both sides coincide. But and about P dependence, it's easy to understand that there is no dependence because it is just a first order pole. So you can at most get some value of some function which does not contain a P and Q, so it is just delta P and Q. If it was a second order pole, you could get a first derivative and it would give some P here, like in the case of free boson. If it is some fourth order pole, you would get some P cube. But in here it is just constant. So, so here is this algebra, and as always, we say that a vacuum is some state where nothing happens. It means that operator expansion of psi around zero, if we place vacuum around, at zero, it should be regular, and it means that all terms with positive p, which produce singularities in this expansion, should act by zero. So here and also here. So uh, and we know that this algebra is a combination of an infinite number of fermionic oscillators. So we have this anti-commutator psi p with psi minus p equals to 1. So uh, uh, so this maybe Fock module is a tensor product from p or p equals to 1/2, 3/2, and so on of such two-dimensional spaces. Like P is vacuum such that it is cued by psi p, and so. Mm, mm, so it's one fermionic algebra, and another fermionic algebra is psi star p, psi minus p, p1. So here we have psi star minus p acting on vacuum. It's for psi star. But we can also generate states by psi, by negative modes of psi. Or something. Or in other words, this Fock space is a span of vectors of the form psi star minus p1, psi star minus pn, psi minus q1, psi minus qm, acting on vacuum. It is the same. There's a different way to write the same statement. So yeah, so we know that a charge of this vacuum is zero because of many different arguments. For example, we can also compute the action of this charge operator expressed in terms of fermions, but it is zero. And charges of all other states equal to the difference between numbers of psi stars and psis, because one increases charge by one, another decreases it by one. So is it fine? Hmm? So charge of this is n minus m, number of psi stars minus number of psis. So are there any other questions about this? So, okay, so if now, then uh, thanks for your attention, and see you next time.